come on, let's have a look. I should close this. The next lesson, I think. Ooh, hang on. Projector in my eye. Gotcha. The next lesson is the Trapezoid Rule, I think. I don't know if you have Moodle there, but I'll just double check that. And the Trapezoid Rule and Simpson's rules, these two rules, that's what your coursework 2 is about. And they're actually they're nice rules for integration. Let me just have a look here. Workbook, Maths Part 2, and Engineers.
How do you know this is the lesson we want? There's no name.
Yeah, though this is Maths for Engineering. This is the bulk of my worksheets in order. So we just did this yesterday. So the next one is, Trapezium Rule. So you can write this down. That's what we're having on the set. Yep, you got that? Okay. So I don't know if this is something you've done before. But here's the idea. Integration can be hard sometimes, and we would like to find a formula to calculate the area that doesn't need to use integration. You know what I mean? So let's just draw some function. Let's just say, I don't know, something like this. And let's say here's A and here's B, and we want to calculate the area. Now, it's not perfect, but what we could do, and let's call this fx. Y equals fx. It's not perfect, but what we could do is we could draw a rectangle, and we could draw a triangle, and we could calculate the area of these two shapes. Like this. You understand? Yeah? So, this one here, its height is FA. There's B, so this height here is FB. Is that okay so far? So you could go dot, 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 dot. So the area would be B minus A times FA, yes, plus a half B minus A times FB minus FA, like that. Is that okay?
Yes.
Yeah, because there's a half the base by the height. What's wrong with you?
What is the base? B minus.
Yeah.
B minus.
Yes.
And F would be the height. Oh, okay.
It'd be okay? Yeah, yeah. So you could maybe you could simplify this a bit, because this would be a half B FB. And this one will be a half B F A. Let me just see if I can simplify this. You don't have to write this part down just yet. B F A minus A F A plus a half, and then we have to multiply this out. B F B plus a half, no, minus a half B F A minus a half AFB plus a half AFA. Don't write this just yet because I don't know if this simplifies. And what can we put together? Do we have a BFA? Here it is here. No, it's not. Here it is here. BFA. Yeah. So that would be a half BFA. Now, do I have another AFA? There it is there. So that's minus AFA plus a half AFA. So that's minus a half AFA. Now, do I have a BFB? No, because this is something different. This is AFB. So I can just say plus a half BFB minus a half AFB. Well, I suppose a half is in everything. So I have BFA minus AFA plus BFB minus AFB, which is a half B minus A FA plus B minus A FB, like that. I took the FA out and the FB out. Yeah? Okay. Don't worry, I'll let you write this down in a second. I want to make sure I can do it first. So what we have here is a formula to calculate this area. But the problem is, in real life, we'll want to calculate much bigger areas. Like, for example, let's just draw something like this. And here's A, and here's B. Or rather, let me call this one x0, xn. And we want to get the area from here to here. So what we could do is we could break this up into many little pieces and use the formula on each piece.
You don't have the x1 like or x2.
Yeah, so here I'll call this one x1, x2, x3, and so on.
You check any value that between them?
Yeah, and what I'll do is I'll call this distance here h, a small distance. So the first one will be x0, and then the next one will be x0 plus h is the next one. Then the next one will be x0 plus 2h.
But there's the h
staying the same. Yeah, x0 is that one, x1 is that one, x2 is that one.
How?
Wait, hang on one quick.
How x1?
What?
How x1 equals x0 plus h?
Here's x0, yes?
Yeah.
Here's x1. And what's the distance between them?
H.
So x1 is x0 plus h. No? Is it okay?
Yeah.
Right, so let's call this piece A1 and this area A2 and this one A3. So what you're doing is you're like making, you're estimating the area by looking at small little pieces of rectangles and triangles. So area 1 would be a half x1 minus x0 f x0 plus x1 minus x0 fx1, where this is like the A and the B. I'm just using this formula here. Area 2 will be a half x2 minus x1 fx1 plus x2 minus x1 fx2. And so on.
No plus h.
Well, yeah, I haven't put this in yet, but I'm going to now. What is x2 minus x1? H, isn't it? And here, x1 minus x0? H, etc. So, because there's a h in everything, I could take the h out. H over 2, fx0 plus fx1. And the next one is h over 2, fx0 plus, fx1 plus fx2. And you can kind of see a pattern here. The next one would be fx2 plus fx3. So if you want the total area, you're going to have to add all of these up. I'll have fx0 just once at the very beginning. And at the very end, I'll have fxn. But what's going to happen in the middle, maybe I'll just draw some more on the side. I have fx0, fx1, fx1, fx2, fx2, fx3, fx3, fx4, and this will continue until the last one, fxn minus 1, fxn. When you add them all up, you'll have an fx0, an fxn, two of these, two of these, two of these, two of these. So you'll, let me just move this more to the left. Okay. So when I add them all up, I'll get area equals h over 2. I'll have an fx0 at the start, plus, and I'll have an fxn at the end, and in the middle I'll have twice fxi, and I'll just write underneath here other. So by other I mean not 0, not n, all the other pieces. I have twice them when I add them up. And you're right, we can work out the xn if you want. So for example, x, I'll write it underneath here, where xi is x0 plus hi. Because you notice here, for example, if I want the third piece, that's x0 plus 3h. So if I want to know what the value of x is, I can use this formula. What's the h though? I haven't said what the h is. Well, if you have a piece from A to B, and you have n pieces, in my picture here, let's say this is A, this is B, the h will be b minus a divided by n. For example, here how many pieces do I have? 1, 2, 3, 4, 5. So the h will be the length divided by 5. Can you see that? Yeah. So I'll write here h equals xn minus x0 over n. And the only thing to say at the end, some books they write x0 is a and xn is b if you want, but you don't have to. I don't want to confuse things too much because I know there's a lot here. This is the trapezoid rule. It's a way to calculate the area without integrating by just adding up different heights. It'll make more sense in a moment when I do an example, but it's an example of what's called a numerical method. Remember when we did Newton-Raphson's formula? What does Newton-Raphson give us? What's it called? What's it called? It's called a root. Yeah, Newton-Raphson gives us a root. Does it give us the exact answer?
No.
Does it give us a very good answer? That's called a numerical method. This is also a numerical method. Will it give us the exact area? No, but it'll be pretty close. The reason it won't be exact is because some of the area you're going to miss. But it'll be pretty close. Okay, so let me just scroll.
So, in the example, I would say roughly or
Roughly. Yeah, so actually if you want, you should really say area is roughly this. Yeah. Or in other words, you can say this is roughly the integration from a to b fx dx, not a to b, x0 to xn, roughly. Okay, so there's a lot here to write down, but that's the theory for this lesson, and we'll look at examples now. I'm just getting the calculator ready. Do you know what would be a better word than other? Middle, because it's all the middle terms except the first and the last. So I'll just write MID. How are we doing? Nearly have that?
Yeah.
Let's have a look at an example. Yes? Adnan? So where's he at? No WhatsApp from him? Maybe he's out buying flowers. Maybe he's out buying flowers. Hey. I'll have to buy them later. Done? Okay. Scroll down. Now, let's look at a question where we know the answer and let's see how good this method is. So let's pick something very simple like a quadratic. And let's just go from 0 to 1, x, y equals x squared. And I want this area. Okay? The area is from 0 to 1, x squared dx. What's this? 1 over
3.
X from 0 to 1, which will be 1 over 3 times 1 cubed minus 1 over 3 times 0 cubed, which is 1 over 3. Okay, let's use our new formula to see how good it is. So, how many pieces should we break this up? Well, let's keep it simple and let's just do 4 pieces. So 1, 2, 3, 4 pieces. Okay? So the first thing you should do is work out the h. 1 minus 0 divided by 1, 2, 3, 4. That would be 0.25. Okay. So what's x0 here? 0. x1? 0.25. x2? 0.5. x3? 0.75. And the last piece, x4? 1.00. Yeah, 1. Okay. Now, besides this, we should also work out what the f is. So we have fx0, fx1, fx2, fx3, fx4. Okay. 0 squared? 0. Now, the calculator. 0.25 squared is 1 over 16. This one here will be 1 over 2 squared, which is 1 over 4. This is 9 over 16, and this one here, 1 squared, is 1. And the rule is, the area is roughly h over 2, so that's a quarter over 2, which is, yeah, an eighth, 0.125. And then we have the first term, which is 0, plus twice all the middle terms, plus the last term. Let's add these three together. 1 over 16 plus 1 over 4 plus 9 over 16 gets 7 over 8. Multiplied by 2, so that's 7 over 4. 7 over 4 plus 1, 7, 8, 11 over 4. So that's 1 over 8 times 11 over 4, which is 11 over 32, which is, and remember the true answer is 1 over 3, which is this. So let's see how close we are. It looks good. 11 over 32, not too bad. 0.344.
But why we get a bigger number? We should get less.
No, because if you picture here, the line is above the curve. It's because the curve is shaped like this. We're counting too much in the formula. This is why it's over. If the curve was like this, yeah. Now, that's not too bad, and this is only using 4. If you think I use more terms, will it improve or not? It will improve. Well, let's see. I'll use Excel. But anyways, here's our first example. Now, sometimes we'll see. Don't worry. I'm glad you're thinking about it, but we'll see. We'll see. We'll see. Now, the other thing I'd like to do is calculate the error. Now, you can only calculate the error if you know the true answer. So I do. Let's calculate it here. So the error would be 0. Well, it'd be 11 over 32 minus 1 over 3 over 1 over 3. Value minus true over true times 100. You probably did this in chemistry as well, and we might have mentioned it in physics, but I just don't remember right now. The error is a reasonable 3.125% error. Not too bad, I don't think. Okay, now you can write this down.
But if we have a lot of like different pieces, this one 1 minus 0, when we divide by let's say 6, it will be 1.6, not even close to 0.6.
What would be 1.6?
0.16. The H.
The H would be different. Yeah.
Be like much different.
But so would all the F's, because all the X's will be different because you're going up in a smaller number. So the X1 wouldn't be 0.25 anymore, it'd be 0.17. So, but I'll show you in Excel, because Excel is easy to type this, yeah?
In the exam, I can save it into as many as I want.
In the exam, they usually tell you how many pieces to take. Now, actually, sorry, I'll stop you right there, Adnan. Before you write this down, I also wanted to show you how you can make this table in your calculator a real time saver. Watch. You type in mode table, which is 7. You type in the function. In this case, it's alpha x squared. Got that? You type it, and ignore this, this option isn't on your calculator. You type in where you start. So here we start at 0. And where do we finish? 1 on the x. Yeah. And then the step is the h, how big you move each time. So how big do we move each time?
0.25.
0.25, correct? And you see you get the same numbers, although they're not fractions, they are the same. Like for example, 0, 0. This will be 1 over 16. 1 over 4, 0.25. You see that? This is 9 over 16. And then what should the next one be? Underneath this?
1.
So this can really save you time in the exam. Because if I look at this, I have no way of knowing if you type them in one by one on your calculator like I did, or if you just use the table, you know. So you won't lose any marks, because in both cases I see the same thing in your answer book, so it's fine, as long as you don't screw it up on your calculator. Okay, now you can write it down.
I will apply one.
No, you need to buy one. When you're ready, I'll do this in Excel. You start at 0 and increase by 0.25.
No, the f of x here.
Oh my goodness! Take these numbers and put them in here.
Just
Yes, of course, like normal. No, not this is normal. What watch is that?
My brother,
Yeah, but what's the brand?
police,
Huh?
police,
P-O...
L-I-S-E,
Like police, as in like law enforcement.
I assume,
Yeah, but the display, is it digital or?
no,
It looks nice. 5 ATM. What's ATM?
Atmospheric pressure.
So it can handle 5 atmospheres. So this is good to know when you're deep water diving. No, because it's really big. So I was wondering why it's so big, but it's like heavy duty.
So you can wear it while you are swimming.
Yes.
I can too.
All right. Let's have a look at this in Excel, because like I said, if we have more pieces, it should be more accurate. Let's have a look. So, let's break it into 100 pieces and see what happens.
Number less than 0.345.
I would hope so. But still more than 0.333.
Yeah.
Yeah. It would be very close, I would hope, at 100 pieces. Let's have a look. Here we go. Right, so here I'll write x, and then that's x0, and we'll go to x100. Now, the h equals 1 minus 0 over 100. So x0, where do we start? At 0. And then what will be x1?
0.00.
Yeah, it'd be this number plus the h. And then, the heck? This number plus the h. There we go. And the next one will be 0.002, 0.003, and then where should we finish? 1.0, which we do. Okay. And then beside that, so this is the, I suppose this is the x, this is the xn, and here should be f of xn. So this would be 0 squared. Then the next one would be 0.01 squared, and so on. So what do we need? We need to know the first, which is that piece, the last, which is that piece, and twice all the middle numbers. So what I'll do is I'll just write it here, sum all of the middle pieces, but of course I also have to multiply it by 2. So I have this number, and this number. And so my area, what's the formula? It's h over 2, yeah, the first plus twice the middles plus the last. Oh, I know. I mistyped. I forgot my multiply sign here. Okay, let's see what we get. Not too bad, because the true answer is 1 over 3. So the error is, let me see, it's this one minus this one over this one times 100. It's not even 1%, it's 0.5% is the error now. Oh my goodness, actually you're right, this is already converted. It's not even. 0.5 would be half. 10, a half, a 20th, a 200%. Tiny error, tiny error. So as we increase, we get more and more accurate. Yeah. The reason we have to study this is because in engineering there's actually some integrations which are impossible to do. I'll give you an example. This seems like a simple problem. Seems not so difficult, right? It's just e to the minus x squared. But in fact, this has no exact answer. You can only calculate this approximately. You can never get the exact answer here. There isn't one. I know.
Why?
Because there's no method that will integrate this.
But we can say 1 over 2x e. 1 more.
What do you say? 1 over 2x e to the minus x squared?
Yeah, minus.
Yeah. Now, when I was in school, sitting down listening to my teacher, I taught the exact same thing that you taught, but this doesn't work. This only works when it's a kx, a linear. Watch what happens if I differentiate. If I differentiate this, it's the quotient rule. So it's the bottom squared, the bottom times the derivative of the top, minus the top times derivative of the bottom. No way does that equal that. So this is not the integration of this. So you could try different things. You could try u equal to minus x squared. No good. Doesn't work. You could try putting a 1 in here and using by parts. No good. All these methods fail. You can only approximate the answer roughly. You can never get the exact answer. On your calculator, you notice that you have a button that integrates. Most of the time, this button is actually just using something like the trapezoid method to calculate the integration. Except maybe it uses 1,000 pieces instead of 100. So it calculates this as the answer, but this isn't the exact answer. Maybe it's right for 4936. Maybe it's right to here even, but then the next term is wrong. It's not the exact answer. In fact, you can never have the exact answer here, only the approximate answer. Do you understand? Yeah. So this is important in engineering. There is another method which we'll look at maybe another day, but this is one of 2 methods in your coursework. What you'll need to do in your coursework too is you need to compare the methods. So if you think about this method, when would it be good for what type of function? What do you think?
Linear.
Oh, it'll be perfect for linear, because if you have a linear function, then this method will just do this. It'll be perfect. What about something like this? Good or bad? It'll be quite bad, because this area, too big or too small?
Too big.
Too big. And then here, too big. This one, it's okay. It's not so bad. Yeah. And this one here, I think will be quite bad, especially if you pick the wrong H. So if you pick the wrong H, you would get something like, I want to pick the wrong one, so if I start here, too small,
How can I fix that?
If you make it small enough, you could go like maybe in a couple of pieces, you know what I mean?
You mean
The H is not small enough.
so like this height. You could put bracket in many.
Oh yes, many. Yeah. And then something like, if you don't have enough pieces, you can be very wrong. For example, here, if you only had, let's say, 1, 2 pieces, it'd be here to here, and you're way too big. But here to here is a little too small. But this is a big error. You're way too big. You need at least 4 pieces, you know, like here to here, here to here, here to here, here to here. Yeah?
How can I get it here?
You can't, no. So, anyways, my point is...
No, I mean like close it.
No, the best way to think about it is the more pieces, the better. Because you can never have too many pieces, but you can always have not enough.
Can I like look at it from the opposite side and calculate the unwanted piece and then minus the whole square area, which is easy to do?
Calculate which piece?
The red one.
Here?
Yeah.
How would you calculate that?
Is it impossible?
No. The whole point of using this method is to reduce your work, not to add to it. Do you know what I mean?
It's the same thing.
What were you thinking of doing here?
Like I will get the whole square area, and then I'll get the smaller area.
This one?
Yes.
But how would you get this one?
Is it possible? Impossible.
Not impossible, but you'll have to integrate. And the point is you're trying to avoid to integrate. Anyways, I simply want to make the point that you can sometimes have not enough, but you can never have too many. You wrote this one down and I showed you in Excel. So for your coursework, you're going to have 2 methods that you're going to need to compare. The trapezoid method, which I just showed you today, and maybe today or maybe next time, Simpson's method, Simpson's rule, which is a little bit more complicated, the rule, but it's a little bit more accurate, but maybe not always, because it kind of depends on the shape as well. So as you notice, if you have something that's linear or nearly linear, this is a very good method. But if it's curved, maybe it's not. You know. What was I saying about the coursework? Yeah, so you have to compare 2 methods, and then I give you a third method which you haven't seen before, which you have to kind of do a little bit of reading about in your coursework. It's a very simple method. It's very simple, simpler than the other 2 methods, but it's kind of a modern method because you can only do it using computers. Whereas with these methods, you could do it without a calculator, you know, just pen and paper. Whereas this new method, it's a modern method that uses random numbers, which I explained in the coursework. So you have 3 methods to compare.
So give us like number and...
Yeah, I'll give you, yeah, exactly, yeah. I'll give you a function, and I say use this method, use this method, use this method, compare and discuss which method was best, which method was worse. So, in some ways, it's maybe a little easier than coursework 1. Do you remember coursework 1?
Yeah.
Huh? It was hard. But this method is a little bit more, here is your equation, solve it using these methods, compare the answers. It's a bit more straight to the point. It's your reward for sticking with the course. Might not feel like it. Yeah. Okay, so I think what we'll do is, I'll just want you to try one, and then after you try one, we can have a look at a tutorial if you want. So the very first one here in the the coursework is quadratic, but I actually did that one. So, and I used, what did I use? 4 pieces, wasn't it? So I'd like you to use 3 pieces to do this one, which I said a moment ago was impossible to do exactly, but you'll be able to calculate it using your trapezoid method. And you should get an answer that's nearly 1.5. I think your answer will be a little bit too big, so you'll probably get something like, no, I think your answer, will be a little bit too small, so you'll probably get something like 1.4. So just try number 2 using the Trapezoid Rule, and I'd like to see what you get, and then we can have a look at the tutorial, okay?
You don't have to make a like a video process tutorial. I just want to know how the function would be. If it's invertible, it's bijective. I think it's bijective. It's 1 by 1 into. I know how to make it into. How can I make it? I know how can I make it 1 to 1. How it's into. How the range is equal to that.
Okay, well, I'll do a couple of examples in a few minutes. Yeah? I'll stop the video then.